Good morning, everybody. I'm Andrea Marchi. I'm Cinespace CEO and co-founder. And now I'm going to have a different set of mic. Perfect. I'm Italian, so just a bit more Latin blood here. So we are an object storage provider, and there is something innovative about our solution. So I'd like to take the next few minutes to explain you and to go through what we did differently. First of all, why object storage? About 80% of the data in the world is unstructured, so we're talking about files, not databases, and these are perfectly able to be stored on object storage. Another key point as we're speaking about application is that object storage is consumed directly by applications, whilst block storage is consumed by operating systems. This makes it intrinsically scalable as you can grow number of clients without needing to grow operating system. Another key point of object storage is that needs and requires metadata, and this is something that will solve the solution for organization of so many data. We're talking about, in 2020, 40 zettabyte of data worldwide, so that's a huge amount of data. So without metadata to organize them and to find them quickly, it's going to be very difficult to find anything. So what have we done differently from the others? We, in 2012, we challenged ourselves to find a solution to store every single data in the world. We started looking around for the technology that was available, and we soon realized that it was basically impossible to do it with normal traditional servers. So we started looking at a more distributed type of technology, and of course our eyes turned to smartphones that everybody have in their pocket. More specifically to the technology that runs them, so ARM technology. The second challenge was how to make these independent cells work together. So one of the staff that was working with us was a biologist. He's a biologist, he's not dead, but he left because now we went too much into details. And he basically taught us how the brain works, and we got inspired from this. And so we created what we can call an organic file system. Allow me to go a little bit more in detail. So, as I said before, this is the first microserver ever built with an ARM CPU. It's a complete server in 8 centimeters by 3. You have a CPU that is specifically built to store data. In the FPU of the CPU, there is already the mSATA plugin that basically you don't need any calculation to write or read the data from the disk. It has got 2 gigabyte RAM, and also 2 Ethernet switches, making it directly connected on the internet. So basically, there's nothing between this and the client that requests for the file or puts the file in. Of course, being an ARM technology, it is very high efficient in terms of energy because it needs to run on battery. Usually it's inside a cell phone, so it's very low power. Everything around it has been developed by us in order to manage data. So it's not like a Raspberry Pi that needs to do a lot of things very different. It's just very specifically built for the purpose. We have another building block, which is to put 1 microserver per storage unit. Whether it's a hard disk, whether it's an SSD, that doesn't matter. It works on both. So we basically plug a microserver next to a disk, and this becomes a full integrated node, which directly delivers the data to the user. We stick 500 of these nodes inside 1 rack, and this allows to have a very high density. In one single rack, we reach 4.4 petabyte, but also 500 different cells that are working in parallel in order to reply to requests or to gather your information. All cells working in parallel allow us to reach high throughput, and which is the key point for an object storage. In order to make these independent cells work together, we had to review a little bit how the file system behind works. And so we developed a fully distributed file system. This is a file system that doesn't reside on a single cell in order to organize themselves, but it's basically each one of them has the full knowledge and talks directly to another cell, and the whole group of cells organize themselves, talks to each other, works as a whole team, just like our brain cells in our brain. There is not a single point of failure. There is not a single controller that tells them what to do. And in case of a death of a node, of whether it's a disk or the microserver itself, there is basically 500 other nodes that take over that work. 500 if it's only one rack. It could be 5 racks, so it's 2,500 and so on. This makes the impact of death of 1, 2, or 3 cells really as a negligible point. Of course, there is a technology which we call actually brain that makes the data move from the dead cells towards towards working cells. Another key perk of this type of technology is the fact that there is no need to intervene when you add new cells. So they automatically, when they automatically turn on the cells, they get an IP, they decide where they are, and they start working without having us to do. So this is very easy to scale and very fast in terms of intervention. What is the result? The result is efficiency by design. So we worked to efficientize every single step of the cloud storage, from the power, that's thanks to the ARM technology, to the hardware. We, of course, customized our own hardware, and we use consumer components, making it lower cost. We are very dense, so in a 1.2 meters, we put 4.4 petabyte. That allows to reduce the cost of colocation, whether it's our cost direct or whether it's a client's cost. And we also have close to zero maintenance, or I'd say zero, but I would be too quirky. Close to zero maintenance costs, because we don't need to intervene when there is a failure of hardware. All of these means that it's basically more efficient and more cost efficient than competitors. So just to give you an example, we are about 1/4 of the cost of Amazon, about 10 euro per terabyte net, or 3.6 euros per terabyte raw. So that's the whole design that allows to reach these price points. Another result is the enhanced reliability and the durability of the data. Thanks to the fact that they are all distributed, the information is distributed and chunkerized across many disks. This makes it very solid. We reach the famous 9 nines after the comma, so 99.99s. And this is thanks to the number of nodes that are working together and making it very reliable. In terms of security, on top of HTTPS, the dual token and so on, which are basically standard at this point, we offer end-to-end encryption. So the data is encrypted locally, data is stored encrypted, transmitted encrypted, but the key is not transmitted. That means that only the user that has the key can access. So even if the data is sniffed or somehow caught, then the data is still encrypted. So there's no possibility of them to access it. We are, of course, eco-friendly. Thanks to the ARM technology, we reach very high energy efficiency level. 1 terabyte is only 4 watts to store. That's about a third compared to a normal technology, a traditional technology. 1 rack of 4 petabyte can be powered by 2 plugs, 2 normal plugs. Of course, we don't recommend it, but you can actually power it via that. And this is because it's only 7 kilowatts of total energy consumption. That is quite low for that amount of data. The result in terms of impact on the planet is that for every terabyte stored with this type of technology, you save 75 kilograms of CO2. That is the absorption of 3 adult trees every year. So 1 terabyte equals 3 trees. Remember that. We are also 100% European. Our data centers are in Europe. Data will never leave Europe. That's in line with the GDPR. the data protection regulation that is coming out in May 2018. And this is key for all your very important data not to be sniffed by our friends in NSA. So just to close out, what can we do for you? In the last day, we'll be speaking about applications and sync and share and usage of storage. And we are a very cost-efficient type of storage for all the applications that you have been talking about, thanks to the different layers of integration, like APIs, which of course are S3 compatibles, or SDKs, software development kits in basically all the languages. We can integrate our service within your application. We are, of course, secure and durable, yes, but also we offer the service as public cloud or private cloud. Public cloud is the usual IaaS, like Amazon and so on. The private cloud is we install a rack inside your data center in order to deliver the service directly from the local data center, so a connection with LAN and so on. I think I am done here. I try to recover a bit of the time. And so if you have any questions, otherwise, we are around, myself and my colleague Filippo, for any further questions.
Thank you, Andrea.
Thank you.
I think we have time for a couple of questions this time. So, David.
What strikes my, as I'm watching this, and one of the things with all scale-out systems, obviously, is that the cost of resolving your data durability and your reliability and so on by redundancy is that you end up paying a penalty in latency. Everything is latency. Many of us have done things like build ARM-based Ceph clusters and so on, and I use Seagate Kinetic chassis as well. Have you measured the impact of, because the other thing that strikes me is in Australia we have a great deal of problems with power budgets. I have to build, I can deploy a whole rack full of equipment and it still has to run within that 7 amps, the 10 amps. What is the effect on latency? How does this fit in with anything that's starting to resemble, high throughput tasks?
So the parallelism of I agree with you. The fact that you're deploying data on multiple nodes might increase the latency. On the other hand, you're replying with 500 plus nodes. So you sequentialize the request by design. So the single file might be slightly slower than a block storage, but given the fact that you are answered by many, you're actually faster on the long run. So we can discuss a little bit more about the performances, but this is basically, we're aiming at parallelizing everything. That's why we chunk file, we subdivide in order to increase the level of parallelization. And so, but as I said, the bottleneck is around 20 gigabit per rack, which we can easily improve it, but for now we never needed to. So that's where we stand at the moment.
Other questions for Andrea?
Hi. Does the system also support tiering with cold data and hot data?
We delegate this type of intelligence to the client. As I said before, it depends on really how you want to develop your client on top of it. So if the system itself doesn't do it for you, but you can do it on the application level. So you can decrease the amount of, for example, redundancy for a specific type of files, or change the setting at a single file level. But we don't do it specifically. Just this is a hot storage. So for cold storage, with a cold storage pricing. So why would you move it to cold storage when it costs just like cold storage, but it's a hot storage? So instead of having the latency of Glacier, you have a hot storage, but with the performance, you have the performance of hot storage with the cost of cold storage.
Other questions for Andrea?
So your microservers are very efficient and run at 1.7 watts, but you foresee having disks connected to them. The
Yes.
disks usually consume something like, I don't know, 4 to 8 watts.
Yes.
So it's one disk per server, right?
Yes.
Or, okay. So you could save a lot. Just picking up on this cold storage and tiering issue, you could save a lot, in fact, by powering down the disks. But it's probably hard to design a system where that would make sense at scale, to notice when, I don't know, parts of the system have become cold and powering down that. Have you looked at that?
We haven't looked at it because we haven't had the need yet for tearing down or to move towards cold storage. As I said, we are more aiming for the hot part. Another option would be to mount SSDs in order to decrease further the consumption, of course, increasing the cost. But yes, I agree with you, we could start developing a system that has parts of it that are more cold and parts of it. But then we would go outside the logic of everybody's the same. So that's one of the building blocks is everybody's the same. We don't want to make distinction. We don't want to be like Trump that makes people look different. Everybody's the same. So this is one of the building block and one of the reasons why also we allow to have such a high durability is to avoid differentiating. We could do racks that are tiering, so we could do one that is hot and one that is cold. That's pretty easy to do. Thanks.
Okay, I think Andrea again.
Thank
And
you very much. Thanks.
we can move on.